Hi everyone, in this talk I will present a joint work with Thatchaphol Saranurak, Deterministic Distributed Expander Decomposition and Routing, with applications in Distributed Derandomization. Let's begin with the computation model. We consider the setting where the input graph and the communication network are identical. That is, each vertex corresponds to a device and each edge corresponds to a communication link. We assume that the communication is synchronous, and the main complexity measure for an algorithm is the number of rounds. We focus on the Congest model of distributed computing. There are two features of this model. The first one is the locality constraint, which refers to the fact that each vertex only has direct communication with its local neighbors. In particular, we assume that the network is initially unknown, and so, within k rounds of communication, a vertex cannot learn anything that is not within its distance k neighborhood. The second one is the bandwidth constraint, which restricts the number of bits that can be transmitted along each edge to be O of log n in each round. Let's quickly compare the Congest model with other models of distributed computing. First, the Congest model is exactly the same as the local model plus the O of log n bit bandwidth constraint. Also, the Congest model can be understood as a variant of the MPC model that has the locality constraint. More specifically, in both of the Congest and the MPC models, the total number of bits that can be transmitted in each round is nearly linear in the number of edges. But the Congest model has an additional locality constraint which restricts who can communicate with who. Let's review some basic graph terminologies. The volume of a vertex set is defined as the summation of the degree over all vertices in the set. The conductance of a cut is defined as the ratio between the number of cut edges and the volume of the smaller side of the cut. Intuitively, the conductance of a cut measures the sparsity of the cut by taking the volume into consideration. The conductance of a graph is then defined as the minimum conductance of a cut over all cuts. Intuitively, if a graph has high conductance, then it is well connected. In this talk, we informally use the term expander to refer to high conductance graphs. A major reason that expanders are useful in distributed graph algorithm is that it allows us to solve a routing problem efficiently. Ghaffari, Kuhn, and Su showed that a routing task where each vertex is a source and a destination of at most linear in its degree messages can be solved in subpolynomial rounds on an expander. The round complexity can be reduced to polylogarithmic if we allow a small polynomial round preprocessing. Using the routing algorithm as a communication primitive, we can let each vertex to efficiently communicate with not just its local neighbors, but arbitrary vertices in the graph. In this sense, it removes the locality constraint of the Congest model, allowing algorithm designers to only focus on dealing with the bandwidth constraint. Using expander routing, many results have been obtained. In particular, a minimum spanning tree can be constructed in subpolynomial rounds on a high conductance graph. This overcomes the square root of n lower bound on general graphs. Given that expander routing is useful, a natural question to consider is to what extent can we apply this tool beyond high conductance graphs? A natural approach to this question is to consider expander decompositions. It is well known that for any graph, we can remove a small constant fraction of the edges so that each remaining connected component has high conductance. And in this talk, we refer to this decomposition as an expander decomposition. There are two questions that we should consider. The first is whether an expander decomposition can be constructed efficiently in the Congest model. The second is whether expander decomposition is really useful in the Congest model. In my recent works with Patty, Saranurak, and Chang, we showed that indeed an expander decomposition can be constructed efficiently in the Congest model. With our distributed expander decomposition algorithm, we gave a nearly optimal distributed triangle enumeration algorithm. The high-level idea of our triangle enumeration algorithm is very simple. We first compute an expander decomposition, and then we use the expander routing algorithm as a communication primitive to enumerate all the triangles intersecting with a high conductance component locally in each component. Finally, we deal with the remaining edges by recursion. Expander decompositions have also been applied to other problems in the Congest model. For example, the first sublinear round distributed exact minimum cut was achieved using expander decompositions by Daga et al. Expander decompositions have also been applied to give nearly optimal solutions for various distributed subgraph finding problems. Expander decompositions can also be used to show barriers to proving lower bounds in the Congest model. The idea of Eden et al. Is that expander decompositions allow us to reduce from the general graph setting to the high conductance graph setting, and then expander routing allows us to simulate a certain class of circuits on high conductance graphs efficiently. Therefore, if we can get rid of an efficient distributed algorithm, then it implies some circuit lower bound, which is believed to be difficult to prove. Now, we are finally ready to discuss the main results of our paper. All previous distributed algorithms for expander decomposition and expander routing are randomized, and so all applications that we discussed before have to be randomized. The main contribution of our paper is to give the first efficient deterministic algorithms for both expander decomposition and expander routing. And so, this enables the possibility of the randomization of many existing randomized algorithms that are based on these tools. Another major contribution of our paper is to give the first polylogarithmic round randomized algorithm for expander decomposition, which we will not discuss in this talk. So, how do we construct an expander decomposition deterministically? First of all, we can make an assumption that the maximum degree is constant by replacing each vertex with a constant degree expander. We can also assume that the diameter of the graph is polylogarithmic by the recent deterministic polylogarithmic low diameter decomposition algorithm of Rozon and Gavari. To compute an expander decomposition efficiently, it suffices to solve the following balanced sparse cut problem efficiently. The goal of this problem is to either find a large sparse cut C or to find a large high conductance subgraph W. Note that the existence of a large high conductance subgraph certifies that we cannot have a large sparse cut, and vice versa. By recursively solving this problem, we can get an expander decomposition in the end. The idea is simple. If a large sparse cut is found, then we remove the cut edges and recurse on both sides. If a large high conductance subgraph is found, then we remove all the edges that are not in this subgraph. In the end, all remaining connected components are expanders. A useful tool for finding sparse cuts is the cut matching game. The cut matching game can be viewed as a construction of an expander in an adversarial setting. It starts with an empty graph on the vertex set V, There are two players. You are the cut player, and the adversary is the matching player. In each iteration, the cut player decides a cut of the current graph, and the matching player decides a matching between the two sides of the cut. After that, the edges in the matching are added to the current graph. In a technical report by Kandekar et al., it was shown that there is a strategy for the cut player that ensures that we obtain an expander in O of log n rounds, regardless of the strategy of the matching player. And the strategy of the cut player is to simply return a sparse cut that is as balanced as possible. To use the cut matching game to find a sparse cut, we can implement the matching player by a maximum flow algorithm to find a flow from one side of the cut to the other side. A path sending a unit of flow from U to B is seen as an embedding of a matching between U and B. If at some point the flow does not saturate all vertices in the smaller side of the cut, then it implies an existence of a sparse cut. Otherwise, after O of log n iterations, the cut matching game returns an expander that can be embedded into the underlying graph using the paths we found in the flow algorithms. The embedding has small congestion in the sense that each edge is used in a small number of paths in the embedding. This certifies that the underlying graph has high conductance. At a high level, our distributed balanced sparse cut algorithm is based on a very recent sequential balanced sparse cut algorithm of Chuzoi et al., which also appeared in Fox 2020. Before describing the distributed algorithm, let's first review the sequential algorithm. The high-level structure of the algorithm is a recursion through multiple executions of cut matching games on smaller instances. Specifically, the vertex set is partitioned into k parts of almost equal size, and a cut matching game is run on each part. The matching player is implemented by finding small congestion simultaneous embeddings of k matchings, and again, this can be achieved by a flow algorithm. The cut player of these cut matching games is implemented by solving the balanced sparse cut problem recursively. So, what happens if the matching player fails to find the desired simultaneous embeddings of matchings? Let's say we still need to match beta B edges. If beta is small, then we add fake edges to the graph to saturate all cuts so that the cut matching games can continue. Otherwise, beta is large, and so a large sparse cut can be obtained. If we are in this case, we remove the cut and start over with the remaining subgraph. In the end, the k-cut matching games give us small congestion simultaneous embeddings of k expanders. And this allows us to consider the graph G star resulting from contracting these k parts into k vertices. And then we can solve the balanced sparse cut problem on this k vertex graph G star by brute force or by some other method that is efficient when the number of vertices is small. The output of the algorithm discussed above will be a sparse cut C such that if C is removed from the graph, then we get a high conductance graph W. So this solves the balanced sparse cut problem discussed above, modulo one remaining issue. That is, the actual subgraph induced by W might not have high conductance because of the fake edges. The good thing is that the number of fake edges is small, and so intuitively there should still be a large expander inside W. Indeed, the expander pruning algorithm of Saranurak and Wang can be used to extract such an expander. So, how do we adapt this approach to the distributed setting? First of all, there are two issues that we need to consider. The first one is that the implementation of the matching player requires an efficient distributed flow algorithm. The second one is that due to the locality of Congest model, we cannot add fake edges to the graph. And moreover, it is not clear whether we can do expander pruning efficiently in Congest. Also, we note that when we move on to the next level of recursion, we will need to consider the imaginary graphs produced during the cut matching game. And the overhead for simulating one round in these imaginary graphs will be proportional to not only the congestion but also the dilation of the embedding. Therefore, in the distributed setting, it is important to make sure that the length of the flow is short. We begin with the matching player implementation. The task that we want to solve is the following. We have two vertex sets S and T, and there is a dilation constraint D. We want to find a maximal set of ST disjoint paths of length at most D. We actually don't know how to solve this problem efficiently deterministically. So we slightly relax this problem by allowing the algorithm to also output a small vertex set B, and the modified maximality requirement is that any ST path of length at most D must intersect B or some output path. This problem can be solved efficiently deterministically using an algorithm of Goldberg, Plotkin, and Baidia. In our deterministic distributed algorithm, we run the k-cut matching games in a non-stop fashion in the following sense. Remember that in the sequential algorithm discussed above, fake edges are added to the graph to make sure that the cut matching games can continue. If we need too many fake edges, then we just stop running all cut matching games and obtain a sparse cut. Here, in our distributed algorithm, let's say if the size of the matching for the cut matching game on Vi is too small, then we just say that this cut matching game fails, and we get a sparse cut that covers a constant fraction of Vi, but the remaining cut matching games with large enough matching can still continue. In the end, we will have a sparse cut that covers a constant fraction of the failed parts, and we will also have small congestion and small dilation simultaneous embeddings of an expander to a constant fraction of the vertices in each successful part. If this sparse cut C is sufficiently large, then we are done already. Otherwise, we discard this cut and try to extend the current simultaneous embeddings to cover as many vertices as possible using almost maximal flow computation. And then we can use brute force to test if they can be combined into a single embedding of a large expander. If so, then we get a large high conductance subgraph. If we fail to do so at some point, then we will get a large sparse cut. Next, we consider expander routing. Our deterministic expander routing algorithm is also based on the simultaneous expander embeddings described before. Note that if we run this algorithm on a high conductance graph, then it is guaranteed that all the cut matching games cannot fail. Given the simultaneous expander embeddings, the routing problem can be solved recursively in a fashion similar to the Gabari-Kunz-Su algorithm. That is, we first route the messages between these k parts and then we recurse on each part. There will be some subtle issue, like the embedding for each part does not cover all of its vertices, but this can be overcome. Another subtle issue is that we need to do a load balancing to balance the message load per each vertex. This load balancing is trivial in the randomized setting as we can simply do a random walk. For the deterministic setting, we employ a load balancing algorithm of Gauche et al. To balance the message load. To summarize, both expander decomposition and routing can be solved in subpolynomial rounds deterministically in the Congest model. Let me conclude the talk with a few open questions. First of all, the ultimate goal of this line of research is to obtain deterministic polylogarithmic round algorithms for both expander decomposition and routing. It is not clear whether this is possible. For expander decompositions, so far we have a randomized polylogarithmic algorithm and a deterministic subpolynomial algorithm. For expander routing, the current results only allow us to achieve randomized polylogarithmic round complexity for routing after a polynomial round preprocessing, and the algorithm is randomized. One caveat of our distributed expander decomposition algorithm is that we actually use a non-standard definition of an expander decomposition in that we do not require each high conductance cluster to be an induced subgraph. And so it is still an open question to design an efficient deterministic distributed expander decomposition algorithm with the standard definition, where each high conductance cluster is an induced subgraph. A reason that we don't have this induced subgraph property is that we used almost maximal flow computation, and so this motivates the next open question. That is, can we find a maximal set of ST disjoint paths of lengths at most d in polylogarithmic rounds deterministically? Note that there is already a randomized polylogarithmic round algorithm for this task by Lotker, Pachamiya, and Petty. Also, one way to transform a given expander decomposition to an expander decomposition with vertex-induced clusters is to use the tool expander pruning that we discussed before. And so it might be an interesting research topic to investigate whether expander pruning can be done efficiently in the Congest model. Finally, in our expander routing algorithm, we make use of a load balancing algorithm of Ghosh et al. To the best of our knowledge, this is the first time this algorithm is applied to the Congest model. It will be interesting to see if we can find more applications of this tool. That's it for my talk. Thank you for listening. I'll be happy to answer any of your questions.